Have you ever wondered why a firework just explodes in a flash, but then an old iron gate takes literally decades to rust over? I mean, it's all just chemistry, right? But it's happening at these wildly different speeds. Well, today, we're going to crack the code on how scientists actually measure, predict, and even control the very tempo of the chemical world.
Okay, let's really look at these two extremes. On one hand, you've got the combustion of propane in a barbecue. It's this violent, pretty much instantaneous release of energy. But then, on the other hand, you have that slow, creeping tarnish on your silverware. That's also a chemical reaction. It's just playing out in super slow motion. Understanding this huge range of speeds is exactly what we're going to tackle.
So this brings us to the big question. It's one thing to say something is fast or slow, but how do scientists put a hard number on it? How do we actually quantify the speed of chemistry itself? That's the puzzle we are going to solve together right now.
To answer that, we're going to need a really solid definition. Because, in science, you can't measure what you can't define. So let's start with the absolute basics and build up from there.
Okay, here is the absolute key idea. We are not talking about distance over time like you would with a car. In chemistry, speed is all about the amount of a substance, the stuff, that changes over a certain amount of time. We're basically tracking how quickly our ingredients get used up or how fast our final product shows up. It's all about the quantity of stuff changing, say, per second.
So, how do we actually measure this change? It's not like you can point a speed camera at a molecule, right? This is where chemists get really clever. They've developed some pretty ingenious ways to track these reactions as they're happening.
And here's that toolkit. Basically, if there's any property that changes during the reaction, chemists can probably use it to track the rate. Think about it. If a solution is changing color, you can measure how fast that color gets deeper, and bam, you're measuring the reaction rate. They can do the same thing with gas being produced, a change in mass, acidity, even how well the mixture conducts electricity.
Let's walk through a classic example. So picture a reaction that's making hydrogen gas. You can actually trap that gas in a tube that's flipped upside down in water. As the gas bubbles up, it pushes the water out. So by measuring the volume of water that's been pushed out, you know exactly how much product you've made and how fast you made it. It's a beautifully simple but really effective technique.
All right, so we've got our raw data. Let's say it's the volume of gas we measured over time. But how do we turn all those numbers into a single, meaningful value that actually represents the rate? Let's dive into the calculation.
So take a look at this. This is data from a real experiment. Notice that at time 0, all we have is our reactant, the nitrogen dioxide. But then as time goes on, look, you can see its concentration dropping, while the products, nitric oxide and oxygen, they start to show up and their concentrations increase. Now this formula for the average rate, it might look a little intimidating with those triangles and brackets, but honestly, it's super simple. That little triangle, the Greek letter delta, it just means change in. So all this formula says is the change in concentration divided by the change in time. That's it. It's just like calculating the slope of a line, rise over run.
And when we go ahead and plug in the numbers from our table for those first 50 seconds, we get this value right here, 4.2 times 10 to the minus 5 moles per liter per second. Now that might seem like a crazy small number, but what it represents is huge. It's a precise quantitative measure of how fast that reaction was going during that specific window of time. But here's where it gets even more interesting. You see, most reactions don't just chug along at one constant speed. They usually start out really fast, when there are plenty of reactants to bump into each other, and then they slow down. So an average rate is helpful, but it doesn't tell you how fast things are going at one specific moment. For that, we need a different tool.
And this is the perfect way to think about it. The average rate, that's like figuring out your average speed over a whole road trip from start to finish. But the instantaneous rate, well, that's like glancing down at your speedometer. It tells you exactly how fast you're going right now at this very second.
So how do we find that instantaneous rate? Well, if we graph our reaction data, it's actually just the slope of a line that just barely kisses the curve at one single point in time. Mathematicians call that a tangent. So a really steep slope means the reaction is going fast at that moment. A flatter slope means it's starting to slow down.
Okay, this brings us to one final and I think really elegant piece of this whole puzzle. We know reactants are disappearing and products are appearing, and they're each doing it at their own rate. But how are all these different speeds connected to each other?
Well, it turns out the answer is hiding in plain sight.
It's right there, inside the balanced chemical equation. The chemical recipe for the reaction, that's what holds the key to how all the different speeds are linked together.
Let's look at that recipe again. Our balanced equation tells us that for every 2 molecules of nitrogen dioxide that break apart, we get exactly 2 molecules of nitric oxide and 1 molecule of oxygen. This isn't just random, it's a fixed, totally predictable ratio.
So those big numbers out front, the coefficients, that's the secret code. Since the ratio of NO2 disappearing to NO appearing is 2 to 2, they are being consumed and produced at the exact same speed. But now look at the ratio of NO to O2. It's 2 to 1. What does that mean? It means oxygen shows up at exactly half the speed. And this is incredibly powerful, because if we can just measure the rate of one single substance, we can instantly calculate the rate for everything else in the entire reaction.
So let's just wrap up what we've figured out. We know that reaction rate is just about the change in the amount of stuff over time. We found out that we can measure it using a whole toolkit of clever methods. We've seen that a reaction's speed isn't constant, and maybe most elegantly, we now know that all the different rates in a reaction are perfectly linked together by that chemical recipe.
And that leaves us with a pretty fascinating final thought. Measuring the speed is really just the first step. The real power comes from controlling it, from speeding up reactions that make life-saving drugs or slowing down the ones that cause things to decay. Once you know how to read the chemical speedometer, you can finally learn how to hit the gas or pump the brakes.